So yeah, I'll talk about domain symmetries and how we can build deep models that can basically use our prior information about symmetries as an inductive bias. So it's very much related to the talks of the first day. Many people talked about invariance and equivariance in deep models. So this is along those lines. What is different? There are two things. One is that I just talked about discrete symmetries, and you'll soon see what those are. And the second part is that we're going to just be constraining the regular feed-forward model in order to make deep models that are invariant or equivariant. So we're not going to design new architectures or new machineries here. It's just about constraining the feed-forward model. And as we'll see, those are just enough to build equivariant deep models for discrete symmetries. Okay. So I'll start with some background in case you were not here for the first day on invariance and equivariance. I'll try to go faster on these. So when we say a function is invariant, what we mean is that we have a set of transformations, a calligraphic T here, that if we apply it to the input of the function, does not change its value. An example of this is something that Shirley talked about. Suppose we want to predict the cosmological parameters, and the model should be invariant to isometries of the 3D Euclidean space, and also to the exchange of the particles in that space. Equivariance is a more general notion that says instead of having one set of transformations, now I have a set of pairs of transformations. So I have a set of pairs of T and T prime transformations such that transforming the input with a T will have the same effect as transforming the output with T prime. Okay? In the case that T prime is equal to identity, then this becomes invariant. So this is a much more general notion. Example of this, again, is something that Shirley was talking about, is in producing cosmological simulations. Suppose you want to, you have the location and velocity of particles at one time step, and you want to produce those at the next time step, but you have this additional structure in your domain that if I rotate everything or exchange the particles, the output prediction should also transform accordingly. So in this case, T is equal to T prime. The same transformation is applied to the output. So it turns out that this T and T prime, or this set of transformations, should satisfy some conditions that we can express using groups. So I'll just do a quick definition of what we need to move forward. So a group, for those who don't remember, a group is a set where we have a binary operation between the elements of the set, such that the set is closed under this binary operation, and we have associativity, and each element has an inverse, and the composition of each element with the inverse is identity. All right, now to define these transformations that I was talking about, we need the notion of group action. Given this group, it can act on a set, calling the set X. So you can think of this group action as a transformation parameterized by the group member. So I'll give you one group member, then given that group member, you take an element of the set and produce another one. For example, the group member is the rotation. I'll give you the degrees of rotation, and you take this picture and give me a rotated version with that degree, right? Now this transformation, this group action should satisfy two conditions. One is that the action of the identity element should be identity function. And the other one is that the composition of the group actions should be the same as the action of the composition of the group members, okay? So in our example, if I was rotating this twice, corresponding to the two consecutive actions, the composition of the actions, it should be the same as if I was giving you the rotation that was basically the composition of the rotations, that is, rotate by 90 degrees. So the notation that I'll use moving forward is that instead of this alpha, I'll talk about, I'll write gx. Gx meaning that g is acting on x rather than I have this function. But you should think of it as having this function defined. Now let's go back to equivariance. What it means is that now I have a function that goes from domain x to domain y, and I have the action of the group defined on both of these domains. These actions can be very different from each other. And what we need is that the action of the group on the input for any group element and any value of the input should be equal to the action of the group on the output. So remember, these two actions are different things. One of them is action on the input, the other one is action on the output. All right? So that's equivariance in its general form. Now, what's the objective of the talk? The objective is that you're given the action of the group on the input and output of a function. So this defines a desirable equivariance property. For example, if I rotate the input, I want the output to also be rotated. Or if I rotate the input, I want the output to rotate in the opposite direction, for example. These are desirable properties that you want for a function to have, and our goal is to design deep models that satisfy these properties. But this is not enough. So it's not enough to have this equivariance property. You also want sensitivity. So for example, take the identity function. F of x is equal to x. It's basically equivariant as long as you define the action on the input to action on the output. This function is equivariant to any group action. So you not only want your function to be equivariant to a set of transformations, you want it to be not equivariant to any other transformation group. And this is something that I guess is missing from all the other treatments of equivariance when people are doing it in machine learning. So you need the sensitivity. Okay, this is something I call unique equivariance, meaning that the function is exactly the right function for our group action. And the scope is, we're just looking at discrete group actions. So the action of the action of a group member on the domain can be written as permutations of the elements of this vector. So it's basically the action of G on X. I can write it as the action on the indices. Okay, so these are discrete actions, what we call discrete action. The same is true for the output of the function. You may think that this is kind of restrictive, but convolution is such an action. It is discrete because it's only moving one pixel to another. It's not interpolating the value of the pixels. So there is a large body of related work, but here I'll just talk about my own stuff. So all right, so what I'll do, I'll give you 3 examples first. For sets, for exchangeable tensors, and for graphs and more general geometric objects like polytopes, where we can use the symmetry of the domain to restrict the feed-forward, the standard feed-forward neural network to be equivariant with respect to the symmetries of those domains. And then I'll give you a generic design procedure so that once you have these group actions on the input and output, you can mechanically design these feed-forward neural networks to have those properties. And you can get the guarantee that you have equivariance. And under some conditions, you get unique equivariance. Okay. So far, people are good? One, good. Jeremy? Sorry? The action of y is trivial, then you get invariance. Yes. Sensitivity, yes. So suppose that your function is invariant to all permutations of your input, as we'll see for the case of sets. Now that function is also invariant to all the translations, because a translation is also a sort of permutation. So this model is good for sets, but it's not really good for images where you have translations. So it is equivariant also to the translation, but that's not good enough because it is equivariant to a larger group of all permutations. So you want the function to be equivariant to exactly the group that represents the symmetries of your domain. Okay, sets. So here's a motivating example. Something is related to what Ravanbakhsh was talking about, but it's a different example. So we have a set of galaxy clusters, And for these, we have some photometric observations. These are like inaccurate observations for galaxies in all of these clusters. But we have accurate spectroscopic observations for a very small subset of these galaxies. And what we want to do is to make good predictions uh, or try to predict these accurate observations for everything that we don't have, like for all the galaxies where we don't observe these measurements. So whatever deep model that we designed for this, and you're already assuming that we're just working with deep models, if I permute the input galaxies, our prediction should also permute accordingly, right? So we want the model to be equivariant to all the permutations of its inputs. And remember, these clusters have different number of galaxies in them. So we can do this with a model that I'll tell you about next, but in this case, for example, we could improve what cosmologists were getting for the prediction of the redshift. So equivariance to set of all permutations of the input. So take the standard feed-forward layer. So we have sigma nonlinearity applied to the product of the weight matrix and the input vector, right? So permutation equivariance is this. We want any permutation of the output of this function to be equal to have the same effect as if we permuted the input. Then we could show this holds if and only if the weight matrix has this diagonal form. The weight matrix can only have two free parameters. Well, you may think, well, that's not good enough. I have very complicated data. The good news is that you could have multiple channels. And you can also stack these equivariant layers on top of each other, so you can build very expressive models of your data. Okay. So one example of where we can use this is for point cloud classification. You have a bunch of points, but you don't really care about their order. In this case, we want invariance, but once you get a deep equivariant model, you do a summation at the top, you get invariance, right? Or any other commutative operation. So in this case, for example, we could get very good results by for classification by directly applying that model to this data set. So here's what the deep model is actually learning. When we look at the first layer and try to see what each of these units is learning, try to maximize its activation, we see that in the first layer, we see units are learning these localized and trivial set of points. In the second layer, we see that it's already learning these non-trivial surfaces that are useful for classification of different objects. Third layer, I couldn't visualize it. The optimization was too difficult. So, all right, exchangeable tensors. This is the next example. So you can think of the set as an exchangeable vector. So the next logical step is to get a matrix and say, all right, I want exchangeability on both sides of this matrix. For example, I want to model the interaction of different forces and different objects. Or I want to model the interaction of protein and ligands. Or I want to model the interactions of users, items, and tags. So in this case, you need a tensor rather than a matrix. So how do you do deep learning with this type of data? In machine learning, the canonical example is a recommendation system. You have users and movies, and you want to make predictions for likes and dislikes. In this case, you again have exchangeability. You don't really care about the order of items on top and on the side, so you can shuffle them around. So in this case, we want equivariance to the action of the product of two symmetric groups. One is shuffling the rows, the other one is shuffling the columns. And we can write the equivariance property that we want like this. These are permutation matrices. Permutation of the columns, permutations of the rows of the output of the model should have the same effect as permuting the rows and columns of the input. These vec and unvec are just basically converting the matrix to a vector and the other way around, so that we're feeding it to the standard feed-forward layer. So this is the equivariance property that we want, and this is again what we show, that if you have this equivariance property, your parameter matrix should look like that. So it only has four free parameters. It has this Kronecker product form. If you have higher dimensions, you have more than two-dimensional tensors, then you get 2 to the power of number of dimensions free parameters. So what is this matrix doing, really? So if you multiply this weight matrix with a vector, what is happening to the underlying input matrix? What is happening is that this is doing pooling or summation over rows and columns and the whole matrix and over nothing. Basically, it's looking at, in order to predict one output element of the matrix, looking at 4 different values over rows, over columns, over the whole matrix, and just the corresponding input, and assigning weights to each of those terms. Okay. Yeah. So how does it work? How do we work with this sort of layer? So this is just one single feed-forward layer, and we have constrained it. We have said that the W matrix should have this pattern in it. Now we could just simply stack these, build a multi-layer perceptron. The only thing is that we have constrained the layer, and we get the equivariance property that we want. And how does it work? It actually works pretty well. So this is the benchmark data set for recommendation systems, and we're comparing to state of the art for these models. And lower is better. We are the green. Our model compared to the other ones are very simple. We just have multiple layers of constrained equivariant, multiple equivariant layers. That's it. These other models, you just have lots of bells and whistles. You see that it's already performing better than those. Some skin fizz here. Oh, there. So it could tell you whether, like, how. All right, yeah. Don't want to be unfair. Thanks. Okay. Moving forward. So I just want to relate this more to physics. Uh, so you could use this to look at the interactions of different objects and forces and try to make predictions by seeing a subset of those objects or force interactions. But another way to model it is the dynamics of interacting objects is to directly look at the interactions of objects and objects. And it turns out that the equivariant model for these 2 types of interactions is going to be very different from each other, as you'll see shortly in the context of graphs. Okay, so one last example. So we have a graph here with 5 nodes and 7 edges. And this is the adjacency matrix for that graph. Okay, so what is the symmetries of this representation of our graph? This adjacency matrix, you can think of it as having attributes for the edges and nodes. You could have node attributes on the diagonal, and off-diagonal elements are edge attributes. The symmetry of this adjacency matrix is that I can permute both rows and columns with the same permutation matrix, and it doesn't really change the graph. So it's invariant to joint permutations of rows and columns. So this is the equivariance property that we want. Permutations, as long as pi here is equal to this pi, we're fine. That is permuting the input matrix to our model will have the same effect as permuting the output of our model, permuting the rows and columns. So it turns out that in this case, you get a parameter sharing layer that looks like that. Now, that also has a nice geometric interpretation, but it's a nice pattern anyway, just to look at. So it has 15 free parameters, but compare this to the model that we already saw. So suppose in the other case, we're representing the same graph, but this time using node-edge interaction. In this case, node-edge incidence matrix, you can use that to represent the graph, right? So in this case, you can apply two different permutations to rows and columns. And in that case, the parameter sharing looks like this. It's a very different parameter sharing. Now the question is, which of these would you use? Because they both can represent the same data, and for each of them, we have a different equivariant model that is exactly equivariant to the symmetries of the domain. And this goes to the higher dimension. So graph is a two-dimensional simplicial complex, we call it. Then we have the triangulated mesh. In this case, instead of looking node-node interaction, we look at node-node-node interaction. An alternative is to look at node-edge-face interaction. For the general simplicial complexes, we call these interaction between nodes the homogeneous tensor representation, and the ones that are between faces of different dimension, the inhomogeneous representation. And then we have polytopes. You can represent the same way, but this time only using inhomogeneous tensor. Basically, you build a tensor that's showing you how faces of different dimension are interacting with each other. And you can have attributes associated with the faces of different dimension. So this is very much related to what Max Welling was talking about. The models we get here are going to be much simpler. I still don't know what's the difference in terms of expressiveness, but there's definitely a difference in terms of representation. So then we have a theorem here that says, all right, so we were talking about expressiveness of these models. For the case of graphs, these both models, we can show that they have the same expressiveness up to change in the number of channels in our deep model and number of layers. But as we go to higher dimensions, this inhomogeneous representation that looks at the interactions of faces of different dimensions, like the node-edge face interaction in a mesh, has a better expressive power. And that needs to become more accurate. I'm just giving you a short version. So we're just more pretty pictures. This is the parameter sharing for mesh data. So our input is a mesh data. We have vectorized it. Now, if you calculate, if you want to consider the symmetries of the mesh data, then your parameter matrix should look like this. But if you're looking at node edge face interaction for the same mesh data, then your parameter matrix is going to be much more simpler. Now, I've been giving you these nice knitting patterns, but you ask, like, where did they come from? Okay, so the idea is very simple. So this is the main idea that leads to all of these design procedures. The idea is that there is a connection between the equivariance property of the layer and the symmetries of the parameter matrix. Okay, and to understand that, let's look at this simple example of 1D circular convolution. If you stare at this long enough, you should convince yourself that if you multiply this with a vector, it's going to do a 1D convolution with a filter size 3. This convolution, for people who have ever looked at the parameter matrix for it. Okay, so what are the symmetries? I'm going to define the symmetries of this matrix as permutations of rows and columns that fix the parameter sharing pattern here. That is, in this case, I'm going to, if we shift everything down by 2 rows and shift everything to the right by 2 columns, we're going to get back what we started from. So pi and pi prime belong to the symmetries of W. So they belong to the automorphism group of W, of the matrix. Then what we could show is that this single feed-forward layer is equivariant to the action of a group if and only if that group is also the symmetry of W. So there is this connection between designing equivariant model and making the parameter matrix symmetric. And it is actually easy to show in one direction. This is the definition of equivariance, but I don't have a lot of time. So good. So this is an equation that Max Welling was referring to as the fundamental equation of equivariance, but that was using irreducible representations. We're using here permutation representations of it. Much simpler. You can get the equivariance property that you want just using parameter sharing in your model. want to get the symmetries in the parameter matrix, we give a procedure how to tie your parameters to make sure that it has the desirable symmetry. So here, for example, we just designed convolution from scratch, but I'm not going to go. Okay, so this dense design procedure um, that guarantees these symmetries is simple, and all the parameter sharing that we saw in the examples that I gave you, you can get it from this design by simply imposing these symmetries on W. But it is also bad because it is dense. So we also have another design procedure called, well, surprisingly, a sparse procedure that reduces to group convolution for a special case where the output of your network is the group itself. Okay, in summary, we can express the domain symmetries, express the domain structure through symmetries in many cases. And when these are discrete, we can impose this inductive bias of symmetry on our model by simply doing parameter sharing in a feed-forward neural network. Okay, and I was asked to give a research question. In all of these talks that we've been hearing about equivariance and invariance, what we assumed was that we know the group, we know the symmetry of our data, our domain. But in many cases, we may not know that, and actually the goal might be to find those symmetries. For example, I give you a lot of real-world images, and the task is for you to find out that these are actually images, that there is this invariance or equivariance to translation in these images. How do we do that? That's it. Thank you.
Of linear maps that are invariant is actually finite and independent of the size?
The size of the group, yes, it is independent. So the thing is that in this case, the only thing that you define is the action of the group on the input and the action of the group on any set that you consider the output of your layer. As long as you give an action defined on the input and the output that you decided what it is, we can do the parameter sharing to make sure that it is equivariant.
Graph, the dimension is 15. But if you have, for instance, a convolution, then the dimension is n.
That's right.
So when is it the case? If I give you a group, can you say before end if the dimension is fixed or if it depends on n?
Yes, yes. So we can calculate that. So the procedure is basically tying the parameters by looking at the orbits of the group action on the matrix. So you can just see how many orbits it has, and you get the number of these parameters. The thing is that the number of parameters could grow, and if it is growing with the n, then the implementation is going to be not efficient for you. So a fully connected convolution layer is really bad. So that's why we had the sparse design. In the sparse design, the number of parameters grows with the generating set of the group. So
do you have some way to clip the dimension?
Yeah, it's gonna reduce rather than size of the group. The number of parameters is gonna in the worst case it could grow to the size of the group, which could be really big, but it actually could grow to it could grow to n2, but what and n2 is the case where you have the fully connected layer with no, like, the group is just trivial group, right? But we can reduce it. So we can reduce it to the generating set of the group.
So I have a sort of proposed answer to the question, or at least a strategy at the end. So like the question is, how do we, I guess, like find symmetries in domains and then exploit them? So here's a little like sort of idea. You could imagine having a model that has sort of it has symmetries, but it also has like a sort of non-symmetry path, like almost like a conv net, and then also like a locally connected net where the parameters aren't shared. And then I think what you need to do is come up with an incentive, like an objective that expresses why you even want symmetries. So, like in this setting, it would be like something like, oh, you have fewer parameters, and maybe you're more sample efficient with your learning. So like if you can express that as an objective, maybe you can cause learning to like essentially use this like available suite of symmetries to the extent that it helps with minimizing that objective.
Yeah, but how do you do it? Because I thought first we could do it by just regularizing the weights so that they're tied together. Incentivize parameter sharing basically by looking at the L1 of all the pairwise combination of weights. That didn't seem to work, so there might be a more clever solution.
Eric, but for instance, yesterday we had this question in Giuseppe Carlel's talk of how to impose the fermionic symmetry. That is, when you permute two elements of the input, it should change the sign of the output. So would your approach work for that? And if not, why?
Okay, I'm not sure. So changing the sign, rather than changing the sign, we could do this. We could have two units, or if you have suppose your output size is m, you just double it. And what we want to make sure is that these two just have opposite, like this is the negative of this. Then we could basically make sure that that happens. So let me try to be more concrete. What I'm worried about that even if we do that, it may not happen. So I was talking about the unique equivariance, meaning that it is equivariant to the group that you want, but it is not equivariant to any larger group. In this case, I'm not sure whether we can get that or not. And if we don't get it, then we won't have that property. So I should think more about this to see whether this happens or not. We could get equivariance for this group or not. So these are actually many of them people have shown. So there was another group who just showed here that the model that we have for the model for the graph and the model for the recommendation system that I showed, where you had different permutations on different dimensions, that those are universal, that they will give you universal approximators for those domains. So they are very expressive in the end if you stack enough of them. Empirically, okay, so for graphs, experiments are still coming out, but for graphs, we are getting better. We are getting a state of the art actually on quantum chemistry data set, which is one of the bigger ones, and also for graph classification on the data set that I think is the largest. I'm not sure. The Reddit data set, it's pretty big. So for that one, we also have a state of the art, but it's still like happening. That's the one. That's the one that's in 3 weeks. Yeah. 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 Yeah.
Learning invariant, we know, at least there are very strong evidence that these networks do it, but it's not clear that they learn the symmetry group. To learn the symmetry group, you need to have all the invariants of the group. So I'm not sure that the problem is learning the group of symmetry, but rather learning enough invariants to solve the problem.
But these are not yeah, if the task is just prediction or building the models, that's probably it. But what if you actually are looking for the domain symmetries?
I understand it would be ideal to be able. I'm just saying, learning a group of symmetry seems to me extremely difficult.
So it is combinatorial in the same way that solving L0 L0 objective is combinatorial, but you could surrogate it and get some, but is it?
Right, you're right. It may be regularization. It's just,
Yeah, but I understand. Yeah, it's a very difficult problem.